All right, let's dive right in. Today, we're going to take a journey down to the absolute smallest scale you can imagine to really understand the fundamental building blocks of, well, everything around us.
This is one of the oldest questions humanity has ever asked. Imagine you take something, anything really, a piece of gold, a drop of water, and you just keep cutting it in half, and in half again, and again. Sooner or later, you've got to hit a point where you can't cut it anymore, right? So, what's left?
And for thousands of years, that's all this was, just a thought experiment. But what's so cool is that ancient thinkers, from India all the way to Greece, they landed on the same incredible idea, that eventually you would hit a single, tiny particle that was literally uncuttable. They called it parmanu or atomos, which means exactly that, indivisible.
Okay, so here's our roadmap. We're going to start with the first real scientific theory of the atom, then we'll get into the rules of the game, how these things actually play together. After that, we'll meet the building blocks themselves, learn their language, and finally, we'll figure out the big one. How do you even begin to count something you can't see?
So, fast forward a couple thousand years to the early 1800s. This is when those ancient ideas finally leap from philosophy into actual science. And the person we have to thank for that is a guy named John Dalton. He's the one who really laid down the groundwork for, well, pretty much all of modern chemistry.
And Dalton's theory? It was a total game changer. He basically said, look, everything is made of these tiny things called atoms. All gold atoms are the same, all oxygen atoms are the same. And a chemical reaction, that's just a rearrangement. Think of it like a dance floor where the atoms just switch partners. Now, okay, we know today that atoms can be split, but his core ideas, they became the bedrock for everything that came next.
So, why was Dalton's theory such a big deal? Well, it's because it perfectly explained a couple of fundamental laws that scientists had already been observing. These are like the non-negotiable absolute rules of chemistry.
First up is the law of conservation of mass. It sounds complicated, but it's actually super simple. You can't just create or destroy matter. Whatever you put into a chemical reaction mass-wise, you have to get out. No atoms just disappear, and no new ones just pop into existence.
And this is a classic way to see it in action. Okay, so you've got this sealed flask with two liquids kept separate. You weigh it. Then you just tilt it, let them mix. Poof! A chemical reaction happens. You can see this new substance forming. But here's the kicker. You put that flask back on the scale, and the weight is exactly the same. Not one tiny bit of mass has changed.
And here are the numbers to prove it. Look at that. The stuff you started with, the reactants, adds up to exactly 35 grams. And the stuff you ended up with, the products, also adds up to, you guessed it, 35 grams. It's perfect. Nothing's lost, nothing's created. The atoms just found new partners.
All right, rule number 2, the law of constant proportions. This one is all about recipes. It basically says that any pure compound always has the exact same recipe, by mass. So water is always H2O. 2 parts hydrogen, 1 part oxygen. It doesn't matter if that water came from an ancient glacier or your kitchen tap, the recipe is locked in. Okay, so we've got the rules of the game down. Now it's time to formally meet the players who are following these rules. The atoms, the molecules, and the ions themselves.
So what's the difference between an atom and a molecule? This is super important. The best way to think about it is with Legos. An atom is like a single Lego brick, the smallest possible piece of, say, carbon. A molecule is what you build with those bricks, 2 or more atoms bonded together. So a single oxygen atom is O, but the oxygen we're all breathing right now, that's a molecule, O2.
And you can see that right here. On one side, you've got a molecule of an element. See, it's just 2 of the same kind of atoms stuck together. But on the other, you've got a molecule of a compound. That's when you use different kinds of Lego bricks, in this case, 2 hydrogen atoms and 1 oxygen atom, to make a water molecule. Same principle, just a more complex creation.
Now, what happens when an atom isn't perfectly neutral? What if it gets a little chargy? Well, then it becomes an ion. An ion is really just an atom that's either gained or lost some of its tiny little electrons, which gives it an overall electrical charge. And yep, there are 2 types. If an atom loses some of its negative electrons, it's left being positive, and we call that a cation. If it grabs some extra electrons, it becomes negative, and that's an anion. And here's a cheesy but super effective way to remember it. Cations are positive, like a cat. Hey, whatever works, right? All right, we've met the players, but how do we write about them? How do we talk about them efficiently? Well, this is where chemistry gets its own alphabet. its own universal language. You can't be writing out 2 atoms of hydrogen and 1 atom of oxygen every time, right? You need a shorthand.
So every element gets its own 1 or 2 letter symbol, kind of like its initials. Some are super obvious, H for hydrogen, O for oxygen, but what I love are the historical ones that come from old Latin names. So why is sodium Na? Because in Latin it was natrium. Why is iron Fe? From ferrum. And gold is Au from aurum, which is pretty cool.
Now, this is a really neat trick for figuring out chemical formulas. It's called the crossover method. Basically, every element has a certain combining power, a valency. Just think of it as how many hands it has to link up with other atoms. So you find the number of hands for each atom, and then you just cross them over. That number becomes the little subscript for the other atom. It's a super quick way to see how things will snap together.
Okay, we've met the particles, we've learned their language, but that leaves us with a giant, and I mean giant, problem. Atoms are ridiculously, unbelievably small, and there are so many of them. So, how in the world do you count them? The answer to this is honestly one of the most brilliant and important ideas in all of science.
And that idea is called the mole. Now, don't think of the fuzzy animal. A mole in chemistry is just a word for a number. That's it. Just like a dozen means 12, a mole means a specific, really, really big number of particles. It's the chemist's dozen, and it's the magical bridge that connects the tiny invisible world of atoms to the amounts we can actually weigh out in the lab.
And just how big is that number? Well, there it is, 6.022 times 10 to the 23rd power. It's called Avogadro's number, and it is mind-bogglingly huge. It's a number so big our brains can't really even process it.
But this is where the magic happens. This is what 1 mole of different substances actually looks like. That little pile of iron filings, that scoop of yellow sulfur, each of those contains that exact same astronomical number of atoms. See? That's the bridge. We don't have to count the atoms anymore. We can just weigh them.
So to wrap this all up, think about this for a second. The next time you pick up a simple glass of water, there are more molecules of water in that one glass than there are glasses of water in all the oceans on the entire planet. Let that sink in. It just makes you wonder, right? If things are this wild and complex at the very smallest level, what else are we missing?